audio. Awesome. There's that. Awesome. Okay. Share screen. Good to see you, Farius. Thanks for joining. We're going to start around the same time, 12:05-ish. So grab some popcorn, grab a coffee.
Oh, I'm jealous. I should be there.
I'm sorry?
You got popcorn, you said?
It's a little hard to hear you. Maybe if you type in the chat, it'll be a little bit easier. Or, yeah, I'm not getting your audio very well.
Do you mind to share the code for last week?
I'm sorry?
Do you have the Python code for last week?
Python code for last week. Yeah, that is a good point. I'll
Do you have
I'll
the
send
link
that
code?
to you after this. I can send it to you. Do you want it now, or do you want to wait until after the presentation today?
Anytime you can. Oh, do you have my email, right?
I have your yes, because signing up, you have your email signing up, right?
I'm gonna send you my email.
Okay, perfect.
Okay.
I'll do that. I'll also set up a public thing so everyone else can grab code from there, but that's a good point.
I just send you my email.
Perfect. Okay, I got it. I'll good to see you again.
Hello. Hi, how are you?
How's it going? Hey, you got in by yourself this time.
Yeah.
That's nice of you. Good to see you, Gavin. Good to see
How
you,
you
buddy.
doing?
Doing well.
Thanks for last time. I appreciate it.
Hey, yeah, no worries. Let me know if you need a ride again.
Okay.
Yeah, all you. I have an email.
Still have your contact. Can you get your contact information once again, please?
I love how the screens display this.
They're nice.
That's so convenient.
Are you in computer science as well?
Yeah, well, software engineer.
Cool. So you're gonna code along with us?
It's Python, you know Python.
Oh, yeah.
Well, each week is a different project, so I don't know
We'll
this
see.
project.
You
It's
missed
always a surprise.
week one, it might be a little tough, but.
It's okay.
Oh.
Is it like
Yeah.
a really build like type thing that builds onto each other?
We're using, it's, no, we don't have one big coding project, but it's the content. We solve like a different problem every week. Kind of need a little bit of information. That's stuff. Maybe get the full comprehension, but follow along, see what it is.
It's okay if I pick stuff, you can pick it up. It's just say hi.
Yeah. The one fear is sometimes with this device, the HDMI is a little finicky, so it like boots me out. That's why I'm like,
Don't touch it. If it works, it works.
I'm typing on my computer very lightly. It's the idea.
You get to zoom, so I can actually see who's there. Why did I connect to I mean, technically, if you're socially distanced from the people around you, you're allowed to take off.
Okay, perfect. How's the Halloween event? I heard about that. Showcase? It's Friday?
It's next Friday, the 29th, yeah.
Awesome. What's happening?
Supposed to be a haunted house down here, but we're having some problems with Kathy,
Oh,
not liking the fact of hosting it in Reynolds, even though it's already been approved by SCR.
really?
Yes,
So what's the issue with it being hosted that
she's
way?
not giving me an issue. She's just telling me no.
Oh, what? That's annoying.
I know, so we're trying to get it figured out because we feel like there's a lot of attention drawn to the event already. So would
Yeah.
it make sense to cancel? Because the only reason we started advertising it is because SCR have approved of it. So the second they approve it, you're allowed to do whatever you want, really.
Unless Kathy
But
says no.
Kathy basically runs the reservations for Reynolds. So if she says no, we can't really.
Can't do it.
Yeah, so we're trying to figure it out.
Good
But
to see you, Gavin, again. We're gonna start 12:05, so grab a coffee. Oh, it's you, of course. Oh my gosh, my mistake. Are you in this Zoom as well, Ivy? I think we have two Gavins.
Gavin, somebody else. Gavin was the Gavin. I'm Eric.
Eric, okay, my mistake. Sorry, Eric.
okay, here we go.
Okay, awesome. Get some people. Awesome. Good to see you, Marie. We're starting 12:05. Hope she heard that. So how have midterms been, Eric?
First year. I just finished both. So,
You finished which one?
I finished both. I had calc and accounting.
Count. You have a minor in like,
Entrepreneurship, yeah.
that's awesome. So are you gonna make a 5-minute company? Ideally.
I'm actually curious. You
Yeah.
mentioned you did a co-op for deep learning.
Yes.
You're like third year.
Yeah, so I'm doing one right now and I did one in the summer as well.
Okay. What courses did you take? So you could do this?
Okay, so they don't provide a lot of good machine learning courses. It's very centric around learning how to program and taking some time. And then optional if you want to use it for you. The best courses I found were all online. So what I did is I took an online course. I send you the link to it. It's free. It's great. It's hosted by this guy named Andrew Ung, who is a pro in the scene. He's done a lot of great work. He's at Stanford. He founded a department inside Google called Google DeepMind, which has basically worked on AI since 2005, which is way before a lot of people have. That's a fantastic course. From there on, I made my own little projects and stuff, and then I emailed some prompts like I was able to get it. So it's a little tough. There's no direct pathway to get there, but if you wiggle around and you're learning about stuff in the scene, if you're able to develop coding solutions like this, and especially working with Python and working with specifically like PyTorch or TensorFlow, which we're using PyTorch, they're a little similar. Those go a long way because with those you can make your own projects, and making projects like that is a really big thumbs up for trying to get into the scene. Yeah, so are you thinking about do you want to do like a little bit of more like academic, looking for like publishing deep learning stuff, or are you trying to just get an understanding of how to use it in the scene for stuff in the future? Because I know a little bit more of like the academic side, like going in and try to like publish and stuff like that, but I know there's a lot of rooms in the industry as well.
I don't really know. I was just like, I kind of wanted to keep my options open.
Okay.
So I remember you also said there's a lot of math courses that you might have to do as well. So have you done like a lot of extra math courses as well?
Yes, the ones that have been helpful in particular is I know you're doing Calc 1 right now. If you continue that to Calc 2, and then after that is Advanced Calc 1, that has a lot of concepts that are very, very poignant for certain stuff, because that's when you start working with multivariate equation, and specifically deriving multivariate equation is a lot of technical. You work on a long partial derivative. You learn about something called the gradient, which is very fundamental to how these things actually learn. So if you really want to invest yourself more in the deep learning route, math is a very good thing, and also statistics and machine learning work really hand in hand. So I know you want to keep things open, and I think it's great that you're coming down here and trying to learn something new, so you can make a decision about what you want in the future. But But if you really want to like get down there and deep learning, stuff like picking up on statistics, picking up on math is a great quality stat. Awesome. Okay, awesome. Okay, what time is it now? Okay, guys, I know we got some more people in the Zoom. We're going to start in 5 minutes. 5 minutes.
Sorry, I didn't get the
YouTube link. Okay, if you go to, do you have an Instagram account? That's
Yeah.
probably easiest, but if you go to the Instagram account and look at Brain Tank Deep Learning, it's going to be all there. There you go, right there. That's the one. There's a link right there, the link tree, and that has our Zoom link. It has our YouTube stuff right there. So the YouTube that has last week's stuff. I'm also going to be posting the code examples. Because I know Ferry talked about trying to get those available so people can like cross-reference and take a look at that. So I'm going to get those up there today as well. Yeah, no worries. Is that someone's computer fan going on?
Yeah. What we really work.
You expect that from mine, not yours.
Powerful.
Sorry, I'm gonna connect from my Mac instead.
No worries. So go, Benjamin. We're gonna start in 5 minutes, or actually like 3 minutes. Yeah. I think it is a good option. I know we were thinking about just having an in-person component. I think it would it would have taken a lot of people out of the program. Yeah, I think doing it on Zoom, easy, especially on a Saturday. Just wake up. Okay, we're gonna give it 1 more minute. Okay, with that, we are going to start. Okay, so I see a lot of names here, a lot of familiar names, which is great. Welcome back. Thank you for coming. I really appreciate you guys showing up today. I think it's cool, especially because week 2, in my opinion, is when this course is really going to start getting interesting. With week 1 being a little bit of tying together odds and ends, and you know, getting ready to really start doing the cool stuff. This is when we are getting deeper and doing cooler things. So one of the things we're doing, the big one, is we are starting with neural networks. So now we're actually getting into deep learning. Before it was a little bit of statistics, a little bit of traditional machine learning stuff, and now we're really getting into deep learning, and we're going to be doing some cooler things, and we're going to be doing a little bit more complicated than linear regression before. We are also going to cover normalization, a term you may have heard before. It's big in fields of statistics as well, but it is also a pretty foundational tool used in a deep learning scientist toolkit. We're going to talk about training versus testing and how deep learning scientists use it. So, like I said last week, this week we are actually going to dive directly into the problem. First thing we're going to do is go over the problem. So, after the success of week 1 of BrainTank, figures in the tech world have been paying attention. Congratulations, guys. A mysterious wealthy businessman has seen the amazing cow predictor algorithm we developed last week, and now he wants us to use our deep learning ability to make an algorithm for him. He is a collector of rare diamonds and wants us to create a deep learning algorithm to be able to predict at what price he should sell his diamonds at. He has given us a list of information about all of the diamonds in his collection, and he wants us to use that information to make an algorithm that can predict price. Okay, so diving into the data set, we can see that this is a very, very wealthy gentleman because he has 7,845 diamonds of various prices. Some of them go up, you can see over here. I hope people on Zoom can see my cursor. I think they can. We have ranges from $125,000 to $1,700. So he is a big diamond collector. All of the diamonds have different features to them. That is an important word we're going to be talking about a lot, the word feature. So a feature is shape. So they come in various shapes. Carat, which is type of weight, just like in diamond or in gold, they use the same type of measurement. Color and clarity. So we'll go over all those features. Feature number 1, shape. Okay, so there's many different types of shapes of diamonds. Our mysterious collector does not like Aster and Marquise because the only ones he has are cushion, emerald, heart, oval, pear, princess, radiant, and round. Those are all the diamonds he has. He also measures carat, important quality for diamonds. That is the general size of your diamonds. So in our collection, he has diamonds as small as 0.19 carats, which are something you might put on a watch or jewelry, little accent diamonds, to things that are pretty massive. 5.6 carats, that's a expensive diamond for sure. We can also talk about color. He only collects the best diamonds from the top row. Those are the colorless and the near colorless. So he has diamonds of color D, E, F, G, H, I, and J. And when we talk about color for the rest of the course, don't be confused about things. I know you've seen like pink diamonds and brown diamonds are very expensive. We're just talking about the purity of the color and if they're colorless or if they're showing a little bit of that yellowness. Last of all, clarity. There's a lot of different types of clarity. The clearest, best diamonds with no bubbles or internal scratches or different particulate inside it, those are your flawless or internally flawless. They can be very, very slightly included. They can also be very slightly included. And then the lowest ones he has are slightly included diamonds, which are a little bit rougher. Okay, so I'm talking about all of that because we call those all features. They are variable statistics, denominations that can help predict price. So our target is the cost. That's what we're trying to learn about. We're trying to use the fact that a diamond, for example, is round, 0.5 carats, has a color of F. The clarity is very, very slightly included, which is a pretty good diamond. And we can use that to make a prediction about the cost. So ideally, what's going to happen in this class is we're going to build a neural network or a machine learning algorithm or a deep learning algorithm to that we can hand a bunch of information to. We can say, hey, Mr. Algorithm, I have a diamond for you that is an oval. It is has a carat weight of 1.5, a color of D, and a clarity of internally flawless. And it can pick up on those qualities and make a prediction for the price because those are some features that can affect price. So for example, if we're looking at this data down here, okay, we can see top left,
that is how our diamond size can affect price. So you can see as diamonds get bigger, they get more expensive, okay? This is a normalized data set. We're gonna talk about that in the future. So it looks a little bit off, but we'll talk about that in a second. You can also see clarity affects cost. So for example, our flawless diamonds, they are a lot more expensive. Those are your big hitters. Those are what your celebrities and your billionaires are wearing. Okay, and then as they get worse, the price on average tends to go down. We can see that color. Our most expensive diamond is G, so it has a little bit of color in it. It's not completely clear, but it's you can see how that changes. We also have different shapes, how that can affect. We can see that an emerald shape often is associated with more expensive diamond, while something like a radiant or a radiant diamond is a little bit cheaper. Okay, so we can see how these features affect the price, and by using all of this data in combination, how we can come with a great algorithm. Awesome. We are going to use these features to make predictions on the price of each diamond. That is our goal for today. So one of the big things we want to talk about is morphing the data set. That is done very, very commonly because when you're working with different types of data, they don't always work in a way that is best for the machine learning algorithm. And we're going to talk about that for a second. So the one thing we want to do is adjust variables so they have a linear nature, and we want to normalize the data. So normalization, one of the big topics we're going to talk about today. And let's get into it. So one of the things we want to do is on the left, you're looking at the diamond size on the cost. So the diamond size in carats, you can see it starts at 0 and it goes all the way up to 5.6. 5.6 is our biggest diamond. But if you notice in this data set, it is very, very clogged over here to the left. And what can happen in this algorithm is that it can affect our neural network or our machine learning algorithms in ways that we don't expect. So we have a lot of data clogged into a very small value. So if you try to pass a value into our machine learning algorithm, and we'll see that in the future a little bit, if they're all around the same value, that can cause some issues. So one of the things we're going to do is we're going to take each diamond cost and we're going to use a log 10 transformation. And what that does is it spreads our data out a little bit more. So now we can see the difference in a data or a diamond of this cost and a diamond of a different cost. It brings it out a little bit and it gets rid of a lot of those outliers. These are mostly outliers. Those are your most expensive of the expensive diamonds. This makes it a little more palpable to work with. The second thing we want to do is normalize data. So we want all of our features and our target to fall in between the values of 0 and 1. We can achieve that by using this formula up here. You're going to see it in practice. And that is because one of the things I want to get in your brain is neural networks and machine learning algorithms, for the most part, they don't like big numbers. What can happen is if you have really big numbers, if you pass in a number that is, let's say 1 billion, which can happen. You can have diamonds that are worth like $100 million, for example. If you pass in a diamond worth $100 million, it can cause unpredictable behavior in the training phase and cause a lot of nasty issues. So generally what data scientists like to do is they like to pinch the most expensive value and the cheapest value in between the range of 0 and 1. So if you have a cheap diamond that's only $10,000 and an expensive one that is $100,000, you are instead going to crush that down and put those values in between 0 and 1. So 1 associates with the most expensive diamond and 0 associates with the least expensive data. And we're going to see how we're doing that now. So this is what we're looking with originally. Okay, this is our price on the left. You can see the diamond prices, and these are the dollar amounts. So it goes from 0, and then up here is 4 times 10 to the power of 5. So that is around $500,000 ish. But you can see that most of our values are in this little tiny sliver down here, which is an issue. We want our machine algorithm to be able to pick up on it. So doing log transformations, we can see we get a nicer curve like this. There's more even distribution, which is something that our machine learning algorithm will be able to pick up on more easily. We can also see that at this point, once we do the log transformation, the values lie between 5.5 and around 3. What we want is our data to fit in between the values of 0 and 1. So we normalize it, and all of our data fits between 0 and 1. This is a bookkeeping thing to do. It helps your machine learning algorithm learn more efficiently. It isn't super interesting. It's not a super sexy topic, but it does help a lot with what we're doing. So we do the same thing. We can see that the left and the right sets of data contain the same information, but the normalized data is easier for the model to use. So this is very tough. This is very easy. And we're going to go into some examples a little bit more about that. On the left, we do the same thing with the carrots, the weight. The carrots also had a little bit of an exponential property to them. So we do the exact same thing. We take the log of each thing, and now we have a much more spread out data between the values and about -1 and 1. And we're going to normalize that to put the lowest value to 0 and the highest value to 1. So once again, the left and the right sets of data contain the exact same information, but the normalized data is easier for the model to use. We're going to play around with this in person, and you're going to have a much better idea. Okay, so what we're doing is we're basically just doing a direct translation. You can see, you can take $1,700. That's a diamond in our data set. You can put it into the normalization machine, and it becomes 0.0079. So that's near your lowest end. Okay, you can do the exact same. I'll take a seat. You can do the exact same thing in the opposite way. So this is just a translational tool. Normalized values have properties that neural networks love, while it is difficult for neural networks to work with large exponential values like our prices does. Just reiterating on that. Okay, so in general, looking at this, an example is we're going to use that. And in our future, you can see the prices over here. The prices get transformed from $11,000 to all of their normalized values. 0.18, 0.079, that's the diamond we were talking about before. And we also do that with our carrot values, okay? We are gonna do some things in practice again, so we'll do that. Here's where it gets interesting, okay? This is where it really gets cool, in my opinion, is working with these neural networks. We've done some stuff in the past, but this is when it really starts getting interesting. So neural networks, okay? I've shown you this slide before. These neural networks are developed, they were developed originally in the 60s, and they were very biologically inspired. In your brain, you have very small computational units called neurons, and they are really good at solving very easy equations and functions. Okay, so one neuron, you can pass in some inputs, and it'll do a little bit of calculation and pass out an output. In the neuron sense, it uses a little electrical pulses, and they do very simple processes, adding, subtracting. They can come together and create structures that look like AND gates and OR gates, and as computer scientists, that should speak to you. And what the effect is, if you clump all those together and create a very complex process with a bunch of those neurons together, you can create very high functioning, very high smart devices. And the best example of that is the human brain, which is, as I've said before, the most complicated thing that we've ever understood in the universe. It's so intricate and it can do so much. And that's all just coming from little tiny computational units. So I'm going to teach you about the deep learning equivalent of that, which is called also called a neuron. It is also called a neuron, and we're going to dive right into that. The same idea occurs where if you stack a bunch of these neurons together, a small computational unit put on top of each other can do amazing things. And it's these artificial neural networks that are having big gains in fields like, you know, artificial intelligence, like auto driving, and all these fields in deep learning. It's stuff like this that's really making its wave. We're going to go to the next slide. Okay, so the neuron. Let's look at the anatomy of the neuron. So the first thing you have, easy enough, the neuron. The neuron is nothing without inputs. Okay, so you can have any number of inputs, and you'll see when we're working on some of the top algorithms have thousands of inputs going to one neuron. Also, you need an output. So neurons will take in information, it'll do some computation, and it'll create an output. And in fact, it can create multiple outputs. We'll see that in a little bit as well. Right now, we're just going to keep it easy and work with one output. It has weights, okay? So if you remember from last week, weights in red, that means those are parameters. So our model is going to change these numbers, and that's how it learns, okay? These are our parameters. We have another parameter called the bias, and those are very integral to how these train and how these look. So last week we had two parameters. We were doing y equals mx plus b. Our parameters were our m value and our b value. And now in one neuron, we have 4 parameters. So that's what our optimizer is going to change, and that's how we're going to train our data set or train our model. The last thing we have, a little bit of a murky topic, a little bit complex, but important nonetheless, is something called a non-linearity. We're going to get into that as well. So let's go into an example. Remember, you got to remember, parameters are simply numbers. Every single parameter is just a regressive number. It's just a float value when you put it on your computer. What also are numbers are our inputs. Okay, so I now have an example of 3 inputs and weights associated to them. We also have our bias. Our bias is 2.5. Bias is also a little bit of an elusive topic, but it is important nonetheless, but we won't talk too much about it. You just have to know that it's there. So I talked a lot about how it takes a lot of these input values and it does a small computation on them to create an output. And this is what the computation is. Looks a little difficult, especially if you're not used to a lot of the notation, but it is very, very, very simple. All you do is you take the inputs, you multiply them by their associated weight, and then you add up all those inputs together. And then on top of that, you add a bias. So for example, input 1 is 5. We multiply that by 1. That's that computation right there. 0.2 for input 2, multiplied by its associated weight, which is 0.5. We multiply those together. -3, we multiply with -0.75. Once we do that, we add those all up together with the bias. We can see 5 times 1 is 5. 0.5 times 0.2, sorry, is 0.1. -3 times -0.75 is our value 2.25. And then our bias at the very end, our bias happens to be 2.5. So we just add that at the end. If you add all those up together, we've done a little computation and we get the value of 9.85. Now I've talked a little bit about the non-linearity. We take this output, we stick it into the non-linearity, which is a function. And what that does, it'll transform that into a value between 0 and 1. So remember when I said neural networks don't like big values? 9 can be a little bit too big for it to handle. It can cause some issues. So it'll stick that between the values of 0 and 1. So what it does is it takes the value of 9.8, and if you put that into the sigmoid function, you'll get a value of 0.98. And that'll be our output. So we've taken 3 inputs, used our parameters to transform them, add them together, added our bias on top of that, put in our nonlinearity, and we have an output. So that's a little bit of the process that goes on with a neuron. We're going to talk about sigmoid a little bit. So sigmoid is pretty straightforward. It is a mathematical function. It's used quite a bit in machine learning. It takes an input and puts it in between the values of 0 and 1. And we chose this as data scientists and as deep learning scientists because it has nice properties to them. So if you input 0 right in the middle, you'll get a value of 0.5. But as you input higher and higher values, it gets closer and closer to 1 exponentially. So if you put the value 1 in, you'll get 0.75-ish. If you put 2 in, you'll get about 0.83. And then if you input a very, very large number, so all the way off the screen, it'll approximate 1. On the output side, the same idea happens. If you input -1, you'll get 0.25. -2, you'll get 0.17. And if you put in -100, it'll approximate to 0. It'll be pretty much 0 exactly. So why do we do this? There is a very real mathematical reason. It is very complicated. You have to be working with neural networks for a long time to really understand why it works. It makes your function something called non-linear. So linear problem solving, what can happen is if you have a problem too tough, if you have a linear solution, you can't do anything interesting. If you stack multiple nets on top of each other, it makes the problem non-linear. And that's not very intuitive, but it is important nonetheless. And I've been working with these for a long time and I don't quite understand it. So you essentially just put it at the end of it, know that it works and know that it's great. But the intuition, which is what I want to get you out of you, that also helps, is that you can see these neural networks as inputting a bunch of values and then outputting a true or false statement. So, and we're going to get into that. We're going to have a great example that you're going to see where if it takes a bunch of inputs and outputs a 1, you can see that as maybe being true, inputting a true value. So you can ask a neuron a question and it can say, yes, I think that's great. Or if it gives you a 0, it can say very strongly, no, I don't think that's a good idea. So let's go into an example. Why do neural networks work? Okay, so we have a very simple question. Should I walk my dog today? That is a question that relies on some input. And we have 3 types of input right now. How sunny is it today? We're going to associate a value of -1 to raining and a value of 1 to sunny. Do I feel like I want to walk? No matter how much of a dog walker you are, you should be walking your dog every day, but you'll be more likely to walk outside if you want to go for a walk either way. Okay, so a value of -1 means no, I don't really want to walk today. I'd rather stay on the couch. And a value of 1 saying, let's get some fresh air. Another one is my dog at grandma's house right now? A value of 0 is associated with no, a value of 1 associated with yes. Okay, so now, instead of asking you these questions, let's ask the neural network some questions. So you can see our inputs. These are what we were talking about before. How sunny is it today? We're going to input a value of 1 if it is sunny and -1 if it's raining, and we'll do that for all of these, okay? We have our weights and our biases, and I'm going to give you trained weights and biases. So this is a smart set of weights and biases. I've trained this by hand, essentially. We're going to ignore the bias. It's not important right now, but we're going to see how they work together, okay? So I'm going to give you a scenario. The day is sunny. I would love to go for a walk. And right now my dog is at my house. So let's step through. Number 1, the day is sunny. So we are inputting a number 1. Do I feel like walking? I do. I'm going to input a number 1. Is the dog at my grandma's house right now? Let's check. No, the dog is at my house. So that's a 0. Okay, so let's get the neuron to do some math for us. Number 1 times 3 is 3. 1 times 1 is 1. And then 0 times -100 is 0. So we get a value of 4. Okay. So once we put that 4 through a nonlinearity, remember high values are associated with 1 and low values or negative values are associated with 0. We have a very high value. So we get an output of 0.98. And what we can say from that in this example is there is a 98% chance that you would like to go for a walk right now. It is very strong proof that you would take your dog out for a walk right now. If we change some of the inputs, it might be a little bit different. If the day is normal, I would like to go for a walk right now, and the dog is at my house, we got to change the inputs, okay? So how sunny is it today? It's normal. It's not rainy, it's not sunny. So we're going to input a 0. Do I feel like walking? I don't want to walk super, but I would like to go for a walk, I guess. So instead of inputting a 1, we're going to input a 0.5. Once again, the dog is at my house. So a 0 is great right there. If we input that all into the neuron is going to think for us. And that thinking comes in the form of this math. 0 times 3, 0. 0.5 times 1, that's the second output right now, is 0.5. 0 times -100 is 0 again, adding the bias, which is 0. We get a value of 0.5. And if we put the value of 0.5 into this calculation, into the sigma calculation, we actually get a value of 0.88. So what we can say from that is there's still a likely chance. It looks like you do want to go for a walk. You should be taking your dog out every day, and you do still want to go to a walk. The day is fine. So there's an 88% chance you're going to go take your dog out for a walk. So it is not as damning. It is not as 100% sure as the last one, but it's still thinking like you're probably going to go for a walk. Now let's go back to the original example-ish, but with a little bit of tweak. So the day is sunny. I would love to go for a walk right now. Sounds really good. but the dog is at grandma's house. That sounds like it could be an issue. So if we input that, we're going to do, how sunny is it today? It's very sunny. 1. Do I feel like walking? Of course I do. It's a beautiful day. That's also a 1. But the dog's at grandma's house. So we're going to input a 1. We're going to do the same calculations with these two. We've done that before. That's 1 times 3 and 1 times 1. Together, that's 4. And then we're going to do output 3. So output 3 is 1 times negative 100. So if we add all these up together, it's 3 plus 1 minus 100 plus the bias, which is 0. Don't forget about the bias. And we get a value of negative 97. Okay. Putting that into the sigmoid function, you can see that there's a very, very low % chance you're going to take the dog for the walk today, which makes sense because the dog not being with you is pretty damning evidence that you are not going to be taking the dog out for a walk. It doesn't make sense. So this algorithm is looking at all of the inputs and is saying, if you don't have a dog, you can't take a walk. So that's a very simple example. You're not going to get neural networks any simpler than that, essentially. But it has taken away some truths about the world around us. Even though it is a 3-parameter equation, it hasn't been fed in a lot of information. It's very small and stupid. It has picked up that if your dog is not at your house, it is nearly impossible for you to walk it. The model will predict 0 every time. So this network doesn't know anything about the world around it, but it picks up that it is impossible for you to walk a dog without a dog. Okay, amazing. The day being sunny is a strong indicator that you will take a dog for the walk. The fact that you want to walk is a factor determining if you want to walk your dog, but it's not as strong as other factors. So it's kind of amazing that this simple neural network is picking up on high-level concepts such as sun, the weather, human feelings, whether a dog is at the grandma's house or not. So it's very simple, but looking at the data, neural networks are very good at extrapolating about things in the real world for use. So that's why neural networks are so universally applicable, because if you have the data to train them, they can really morph around any issue. They can pick up on random crazy things that you wouldn't even think of. Okay. So if one neuron is strong, thousands are stronger. So if we use more than one neuron, we could tackle the same problem. You could use the same input. So here are the 3 inputs and create an output. Okay. And you can see that if we dive into these neurons, they're very similar to what we were talking about before. There's our input 1, input 2, input 3. Each of these inputs has a weight and they all output. So how I said before, you can have multiple outputs. What this does is it creates the same number. If this output is 0.95, instead of just outputting it once, it'll output it to a bunch of different neurons. And these neurons have their own weights associated with them, or their own biases associated with them. And they'll be taking information from all of their inputs. So they'll be taking information from this neuron, from this neuron, from this neuron. So you can see why we call this a neural network. We are creating a network of nodes to do small calculations that build up on top of each other to do something quite beautiful. Okay. So this might not be a great example because it is a quite trivial question, what we're doing before with the sunniness and walking of the dog. But if we do something a little bit more complicated with more nuance, there might be reason for us to try to build a smarter system. In general, one thing I would like to say, more neurons can equal more power. That works a lot in general. Okay, if you get too big, there's some issues, but you could do more with a bigger net for sure. So let's get into a little bit of a harder problem. Okay, what if I told you that I gave you a list of 1 million different cities at different time periods, and it gives you information about how close the city is to the sea, what country does the city belong to, and what year it currently is. And what I'm going to ask you is to predict the population of that city given those 3 features. Okay, that's a way more complicated question. Okay, there's a lot of different variables that can affect that. Let's say, for example, what if the year is 1942 and you are in Russia? A big population decrease. You can see year can affect population a lot. Population grows throughout the years at a very exponential factor. There's compounding issues. For example, what if the city is close to the sea and the year is 12,000 BC? that doesn't really affect a lot of things because sailing wasn't invented. But in the year 2020, having a population by the sea is very useful because you can ship things in between. And we have large populations by the sea. So these factors are complex, nuanced, and they build upon each other. What year it is can affect information condoning to if it's important to be by the sea. What country it belongs to can affect things happening with like by the sea, and they compound very strong. So what happens in these neurons is a lot of the time these neurons can tackle a very small problem, and intuitively they can tackle a small problem. You can ask one neuron, does this country have an abundance of food? And what you can look at, it can look at parameters like what year it is, because as you go through time, abundance of food becomes easier. If you, for example, are in Iraq in 12,000 BC, you will have some food because that is where the Mesopotamian rivers are, and that is where some food is now. But if you change some of the variables and you are in Iraq in 2020, now they're dealing with a lot of droughts. Food is less available. That can affect population in a very meaningful way. You can also say you can have another neuron on the same hidden layer is what we call. I'll get to that terminology a little bit. That's tackling a question like, would the city have railroads at the time? Because railroads invented in the 19th century affects if it's important to be by the sea. With railroads, you can move food to places far away from the sea. So how does that affect the population? You can have neurons later in the system that take in those two questions. They take in the fact that this country has abundance of food and railroads were invented at the time, compounds them together, and it makes the conclusion that this country was able to move food on railroads. Okay, so you can see very simple question and answer neurons type ideas can compound to create very intricate and interesting solutions. Okay, so that's why if you look at the anatomy of one of these, we have our input layers. That's the information we want to give our model. We have an output layer at the very end, which is the information we're trying to transform that to. Remember, deep learning algorithms fundamentally are transformers. They take a certain amount of data and they transform it into data that you want to see. And it's the same thing with our brain. Okay, I can look at my friend Sarah over here and there'll be pixel values in my eyes, essentially. I can see little contours in her face, her eyebrows, I can see what type of clothes she wears, and I will use that, and that information will go through the neural network that is in my brain, and it'll transform that complex picture data into an output. And my output will go through my mouth, and it'll be, that is my friend Sarah. Okay, fundamentally, we're doing the same thing with these neural networks. Okay, awesome. So all of the logic, and this is what's great about neural networks, all of the logics that these neural networks can learn are hands off to the developer. Okay, the net will learn for you. So remember when I was saying that they build up on more complicated processes? Imagine if you had to sit down and with if statements determine if it's in between 1939 and 1944, there's a big war, subtract population by a certain amount. Right? That's very complicated for you to do. And there'll be different factors that you won't even realize in your brain that a neural network will be able to pick up on. But as a human, you might have a lot of struggle going through. Okay, so that's why these are so great. Training neural networks. This is where it gets interesting. Okay, so I just want to talk about the data set a little bit, and when we get hands-on, it's going to be a little easier. So we have all of this data here. We have a diamond, for example. Diamond 28 is an emerald. Carat value 0.51, so it's pretty small. Color is G, so it's quite clear, but not the clearest. Clarity, internally flawless. That's a very, very nice diamond. But its price is $1,971. Okay, for example. The issue is neural networks, great with numbers. Numbers and neural networks, best friends. With words, a little tough. Okay, think about trying to put taking this neuron right now, and instead of putting a number, putting a word. Doesn't really work. 1 times IF doesn't mean anything. So what we're going to do is we're going to transform this data to make it a little bit more readable. So remember all of the color codes, D, E, F, G, H, I, J. those get transformed. We're going to use instead this system right now. It's called a one-hot embedding. Essentially, what you have to understand is diamond at index 0. If you go to each column and ask it this question, if you say, is this diamond a diamond D? Does it have color D? If it's 0, no. If it's a 1, then yes. So is diamond 0 have color J? Does it have color J? It has a 1 there? Yes. Okay, these are all unique. So looking at diamond at index 1, you can see that it has a G color. Index 10, you can see it's also a G. And that also extrapolates to shapes and also to clarity codes. So you can see at this diamond right here, diamond index 1002. If we go over, we can see it's a D coloration. Keep on going. It is slightly included 1. And it is a shape of a pear. Okay, so that's how it's going to happen. And we can take all of these, our 24 features. So in total, we'll have 24 variables. And that's what we're going to use as our input to our neural network. Okay, and our target, our price right here, that's what we're going to be trying to predict. So we are going to be using a neural network for that. And our neural network is going to be pretty big. Okay, so it didn't even quite fit in the picture when I was trying to put it in today. We have an activation layer. So that is our input layer of 24 nodes. That's going to be all of our information connecting to the diamonds. And then it's going to go through some hidden layers right here. And this is where the brain is going to happen. This is where it's going to learn about different combinations of carat and shape and quality and all of that and how that affects price. So it's going to be 40, 20, 10, and then it's going to output to one node, and that is going to be our price. So we're going to get a price from there. Check the chat, of course. So in last week's problem, did we just build a single neuron? Yeah, you can actually say that we did. It was quite similar. We didn't have an activation on the last part, but you can see that yes, the linear component of it, y equals mx plus b. Instead, we're replacing it with weight 1 times input 1 plus the bias at the end, and we can have a variable amount of inputs. So for example, in this one, this neuron right here at the very top, this very small one, is getting input from all of the previous neurons on here. So it is going to be weight 1 times input 1 plus weight 2 times input 2, all the way up to weight 24 times input 24. And that is all a linear system, just like our y equals mx plus b, but just with more inputs. So Dawson, you got it 100% bang on. It is very similar to what we were doing before. Okay, the 3 tenets of deep learning. You guys have seen this last week. We're going to hark on it again. It is universal. Our data set, a set of data that we can that has information that we can use to teach our model to perform better. That is our diamond data set. That is what we're going to use to train our model. Our model, mathematical function, remember, even with all of these parameters and the neural network is very long, very complicated, it is still a mathematical function. Takes an input, creates an output. It takes an input and creates a desired output. It is defined by its parameters. Remember, our parameters are our weights and biases. So if you have 1,000 neurons, you're going to have a lot of weights and biases because each neuron is going to have its own weight and its own bias. We will train those and we'll change those to get a desired result. So ours are going to look like this. Remember, all the weights and biases in the neural networks are parameters. Remember, parameters looking like this are weights, our biases. We're going to have a lot of them. We are going from 2 to something in the thousands of parameters, okay? So you can see how these things can scale up and become very smart very soon. Our loss function, we are going to use the exact same loss function we did last week. Mean square error. Last week, we were trying to predict the price of cows. Now we're trying to predict the price of diamonds. You can see they use very similar reasoning, okay? So we're going to keep that the same. The deep learning flow, we're going to talk about this again, like we are every single week. Number 1, initialize your model. Randomly assign your parameters a value. 2, grab a single entry from the data set, an input and a ground truth associated with that input. Take that input, put it through the model and save the results. Use the loss function to measure how different the result is from the truth. Remember, our loss function is trying to figure out how wrong we are. Give it to the optimizer, our magical robot that will walk into our model and change our parameters. And you repeat steps 2 to 5 many times. Okay, so looking at this flow again, for example, price of data. we have a diamond that with a normalized value is 0.1. It has input features that is essentially a list of 24 numbers. Okay, so that's what I mean when we put it in brackets, 24. Okay, it's a list of 24 numbers. We're going to select one of them from our data set. We're going to grab the top one, put that through our model. So we take those 24 numbers, which has information about what shape it is, what the carat is, different color quantities, and the clarity as well. And it'll output a number. So in this case, it takes this and outputs the number 1.3. Now let's compare that to what it should have been. So our result, we got 1.3. The ground truth, which what it should have predicted given the input features, is 0.18. So if we could take that, the nice thing about normalized values, we can convert them really easily to dollars. A normalized value of 1.3 would be a dollar amount of about $2 million. So very, very expensive and very, very off from the true value, which is $4,371. So not quite hitting it on the head there. We did quite poorly and we should fix that. And we're going to fix it by passing it to the loss function. Working the same way, the result and the ground truth go in. You take the result, subtract the ground truth, and you could square that and it'll give you a result. Intuitively, I want to talk about this again. Our goal is to get our results and our ground truth to be similar, because then it's doing a good job at predicting, given an input, what the diamond cost should be. So a low loss function is good, because if you have two of the same numbers, if you take, for example, 0.18, subtract 0.18, that's 0, you squared it, is also 0. And that means you're doing a really good job. You're getting a bang on the head if the loss is low. If the loss is high, like it is now, 1.2, we are getting very different values. So loss is bad, we want gains. So we're gonna give it to the optimizer. The optimizer will look at the loss and use it to determine how to adjust the model's parameters. We want the loss to be small, and it's going to take that into consideration while morphing around these thousands of parameters. It'll go into every single parameter and play with it a little bit. Perfect. So if we run this again, grab the next data, we can see our input features, also a list of 24 variables. Those variables are going to be different than the one previously. We put that into the model, and now it's predicting 0.77 when the truth is 0.52. Can use the loss again. Remember last time our loss was about 1.25, I believe. Now it's much less, 0.0625. So we are getting better. Our predictions are a lot lower, which is good. We pass that to the optimizer. The optimizer is once again going to look at that and change those variables. And eventually we're going to get something good. So this is our most expensive diamond. You can tell because the normalized value is 1. If you pass it in, now our model is smart. It's taking all of the factors into consideration, and it is finding a good estimate. So 0.99 when it should have been 1. Very, very close. We did our best and we got very, very close. Result minus ground truth. Now we have 0.01 squared is 0.001. We're doing awesome. Bang on. Okay. So training and testing. This is the last topic I'm going to talk about before we get into the coding. Getting our hands on to this stuff. Okay, so how do we know our model is doing a good job at performing the task we are asking it to do? How do we know? How do we know that our algorithm is doing what we want it to do? Okay, so I'm sure a lot of you right now are studying for midterms. So this might bang on pretty true. But have you ever been studying and the teacher says, we're going to go through everything in the textbook, front to back. And so you devote your life to this course. You really want to get 100. You look through it all. You study it and study it until the point where you swear you can recite the book from the beginning to the back. You understand everything fundamentally. Okay? Maybe not to that extent, but to some extent. You know the textbook very, very well. And then you go to write your test, and the teacher gets you a problem that you swear was never brought up in any of the lectures, never brought up in the textbook, and you freeze. Okay? That is trauma right there, and it's happened to me countless times. Okay? So what you're really doing is your textbook is your training set. Okay? You are looking through the textbook, you are learning, and you put a lot of time, and your brain gets very good at adapting and learning how to do everything in the textbook. But once you try to apply that algorithm to the real world, you get slightly different questions and your brain freezes. Okay, so all of the questions of the exam, that's your entire set. Those are all the questions you're gonna see. That's the universal set of questions. You have all the questions in the textbook. That's your training set. That's what you're learning on. The questions your teacher created specifically for the exam, which has some deviations to them, that is your test set. Okay. So I want to give you this scenario. What if you were only good at answering textbook questions, but when new forms of questions appear on the exam, you were unable to solve them? So you might be good at specifically using a very specific form of a function or a type of question. But when you bring onto the exam and you have to use your free thinking a little bit to transform your thinking and solve a different question, maybe an application-based question when before you're doing knowledge-based questions, you can freeze. And that is actually an example of maybe a poor thinker, and maybe you are deserved a little bit less of those good grades because you were unable to think a little bit adaptively. Oh, looks like we have one more person. Okay, so that is an even bigger problem to machine learning algorithms. What can happen so often is these models aren't as good at adapting. So human brains, if you learn an equation in a textbook, it is likely that you're able to morph that into maybe a different understanding, because you can conceptually understand what the formula is doing, what each of the numbers in the formula is doing. And maybe on your next math test, when it changes a little bit, you can have a little bit of an intuition. You can transform that over. Machine learning algorithms are not the same. Okay. If you were training it on 1,000 diamonds, but those diamonds all happen to be small diamonds, 0.5 carats to around 1 carat. If you later hand in a diamond to it that is 5.5 carats, it's not going to know what to do. It's never seen a diamond like that before. It hasn't been trained on it. It doesn't know the intricacies about it. So its mind is essentially going to blow up, and it's going to make a prediction, and that prediction is going to be bad. So as machine scientists, what we do is we take our data set. We have 7,845 diamonds in our set. And what we do is we shuffle those diamonds around, okay? So instead of being ordered, we don't want to be ordered by index number, because index number could indicate something about the data set. We shuffle those diamonds around, and then we'll create a training set and a test set. So we have 7,000 entries in the training set, and we'll have 845 in the test set. And we are going to use only the 7,000 diamonds to train our model, to get smart. That's what's going to give us the intricacies about diamonds. It's going to teach us that D diamonds are the clearest, and maybe they're the most expensive. It's going to train us that bigger diamonds are worth more money. And then at the end, we're going to, once we've trained our model and we think it's performing well, we are going to test it on 845 diamonds to see if it's actually good at understanding diamonds and their intricacies, or if it's just copying the data. Essentially, these diamonds, if you hand it 7,000 diamonds, there's a very real possibility that the model instead simply just looks at the diamond values and puts them into memory, and it can remember, oh, there's a diamond that had carats of 5.5 and had this shape and had this color and this. I remember that is worth that value. We don't want that. We want it to learn. So if you give a new diamond, it can adapt to that. Okay. If our model is able to correctly predict prices of diamonds in the test set, it is a strong indicator that our model has learned the features that affect diamond prices. That's good. That's what we want, instead of memorizing and copying the textbook, which is bad. Okay. So we are going to get coding now. And also my computer is going to run out of battery. I don't think it's charging on the port. So I'm going to see if I can fix that. I don't think it'll ring. Do you have an extension cord anywhere else?
That I will go check for actually.
Okay, I appreciate that. I'm at 20, so I had some time, but I don't know why. Struggling a little bit. Okay, so just like last time, we are going to be using Google Colab. So what I want you guys to do right now is to go onto github.com/braintank-deep-learning. Okay, we're good. Please feel free to say something in chat if you're having some issues. I know we've had some issues in the past. And now we are going to check out week 2. Did week 1, week 2. Okay, perfect, perfect, perfect. You should see exactly 3 files. Perfect, thumbs up. I don't see any issues right now. Go to code. Very simply, we're just going to download the zip file. Bam, perfect. Save it. Cool, awesome. And you should get a file saved. Open that up. Awesome, thumbs up, thumbs up, thumbs up. Let's extract it. You put it anywhere. I'm gonna put it on my desktop. Cool, perfect. Wait, actually, I think my mistake here. Let me here. I'm so sorry. I was sharing my thing. Now I have my screen. Okay, so you should have a file like this. I'll just redo it just so people on the Zoom can see. I downloaded the file, opening it up, click on it. You can extract it to anywhere you want. I went to my desktop, and then you should have those files downloaded. Okay. So if you're doing it right, if you look at my desktop, I should have a folder here somewhere with week 1. Good news on the extension cord?
I need to get the password.
It's okay. It's okay. It's okay. Okay. I actually didn't extract it. My mistake. So I'm going to extract it. Extract all. Perfect. Awesome. You should have the files on your desktop. Desktop. Okay, whatever. Okay, next step. We are going to go to, once again, we're going to be using Google Colab. So if you look up colab.research.google.com, or if you simply just look up Google Colab, very, very simple. The first link will get you to it. 16%. Okay. Cool. Okay, awesome. So everyone has this right here. I don't see anything in the chat, so I'm assuming everything's good. Okay, we've done this before, so you guys should be good. New notebook. Awesome. Okay. Ooh, it's charging now. Okay. Awesome. Now we have a blank space. We are going to upload. So it says upload notebook. Browse whatever it was. Screenshots. It should be on my desktop. Oh, I didn't actually extract it. Yeah, desktop. My bad. I'm gonna just re-extract it just to make sure everyone's on the same page. Awesome. So I have it downloaded here. My mistake. This is not as clean as it should have been. Extract all. I feel like profs always have this issue where they just can't figure out their own project, and I'm going through that right now. So awesome. Desktop. I don't know what the issue is. Okay, whatever. We're good. I think we're figuring it out. Now, if we go to these files, desktop, week 1 master. Okay. Easy solution. Okay, whatever. I don't know why it's not showing up on my desktop. I think it's just an issue. Nevertheless, it doesn't matter because I can just drag in. If you take this week2.ipynb file, drag it in. That's what you need. You need the IPYBN file. That's the most important one by far. The rest are irrelevant. Okay. So do we all have that done? I know my explanation was a little confusing. You guys are good? Perfect. Okay. You're smarter than me. You figured it out. Okay. Awesome. Here we are. So it should look a little bit like this. Okay. I'm going to do a little walkthrough again. First thing you're going to do, click this button, get clone. That's going to get a lot of the information we're going to be using. You see something that says cloning into week 2. Perfect, perfect. Click this folder right here. You know it worked if you see this folder week 2. And in week 2, we have 2 lists, 2 CSV files. So those are like Excel files. And we got diamond list, and we also have another one called diamonds. We'll be looking at that in the future. I'm actually good. I got it. I appreciate that. Sorry about that. So first of all, the first thing we're looking at is we have a list of helper functions again. So to help with data, reading data, this is going to look into our diamond list.csv file. So our diamond list file, if you double click on that, that has a lot of information. Okay. It has all of the diamonds we have, the shape number, a reference number. We're not going to be using those. The shape, that is what we're going to be using. We have price in Canadian dollars, price also written in a more manageable way. Carat values, cut, another thing we're not going to look at. Color and clarity. Okay. We're going to click run on that code right there. Okay. Perfect. So make sure this helper function is running. I also have another helper function that will transform our normalized values. We're gonna have normalized values in our data set. It'll turn that into dollars. So that is gonna be done for you. Don't have to worry about it. Okay, we have 3 tasks today. We're gonna have, we actually don't have to do this one anymore. I got rid of that. So we have 2 tasks today. Perfect. We're gonna be creating a neural network that we can use to predict the value of a diamond given its cut, its shape, color, clarity, and carat. Okay. Our model will have 24 inputs and go through a neural network with 3 hidden dimensions of 40 neurons, 20 neurons, and then 10. Those will all output to 1 output neuron that will predict the price of the diamond. Perfect. Easy peasy. This is what we're going to be doing here. This is what we're going to be building on. Okay. So let's get into it. The first thing I want to show is I talked a little bit about these things called tensors. Okay. So I can make a tensor that's called x.torch.tensor. Okay. And I can give it a value of 5, for example. Okay. If I print that out, you comp sci students should be able to figure that out. Should output a value of 5. Is that working for everybody? We're good. If you get any errors, and some of you guys at home might, I recommend click this one. Click the helper functions again. It won't work unless you click run on helper functions. It won't show anything, but you do have to run it. Okay, so we have this. This has 1 value and it has the value of 5 in it. Okay, we are going to increase the dimensionality. So tensors are good at storing a lot of data. You can store 1 value in it, and that's what we did last time. But now that we're working with so many different parameters, it's important to be able to use lists. And our data set also will be a big list. So for example, I want you guys to get used to something that looks like this. So I'm going to make a tensor and I'm going to say torch.tensor zeros. And then I'm going to input a size. And that size in brackets has to be in brackets. Let's just say 10 and 200. Okay. So now if we run that, there's going to be a lot of zeros, and it's going to come in a 2-dimensional looking array. It's going to be called a matrix. Okay. And that matrix is going to be 10 across and 200 down, or sorry, 10 down and 200 across. So if you want to look at its shape, you can do that. Print x.shape, and that'll give it to you. So the shape of ours is 10 times 200. I want you to read that as a deep learning scientist does. Okay, so a deep learning scientist will take a data set and its application, and they'll translate it a little bit. So for example, this could be, I have 10 rows of 200 different numbers that have to do with car information. Let's say I'm working at Tesla and I need to know car information. If I'm working with pictures, which we're going to be using in the future, we can do something like this. So it's 256, 256. This could mean I have 10 images that are 256 pixels by 256 pixels. That's a 3-dimensional object. Okay, that's called a tensor. You're going to get used to working with this in the future. It's very intuitive. It works very easily. And you're going to become masters at it pretty soon. So let's get started with, first of all, in our steps, data set model loss. Let's play around with the data set. So if we're going to create the data set, what we're going to do is data set equals, and we're going to be using my little helper function, read data. Okay, read underscore data. That is a function. We'll call that, and that is going to help us out. I also want you to print out dataset dot shape. Okay, so we'll look at that. Perfect. Okay, so we read in a bunch of data and it outputted to a shape. So what we have is our data set is 4,845 diamonds, and those diamonds all have 25 rows to them. So remember, we have one target value there. So that's the price we're trying to predict. And we have 24 input numbers. Okay, we can take a look at that. If you press refresh here on this little folder, I'm going to ask you to do that one more time. We actually have some helpful CSV files that I want you to take a look at. So trimmed mystery diamonds.csv. That is our data that we're using right here. So that is, it got rid of all the unnecessary numbers, and this is all the stuff we're going to be using. So you can see our prices, they are all normalized. Our carat values also all normalized. The data set is shuffled. So look at this indexes right over here. 487 is right next to 1,103. It's shuffled for us, which is good. And we have all of our one hot vectors. That's what these are, our little categorical values. So if we're looking at number 487 perchance, we can see it has a price that's normalized as 0.23. So it's a pretty cheap one. It's close to 0. Carat is also quite low, 0.17. And its color is H. So it's a little murky, but it's still quite clear. It is very slightly included 1. So it has a few abrasions on it, but it's still pretty good for the most part. And it is a shape of an emerald. Okay. This is what our data is going to look like when we're using it. So perfect. We can close that up. We have our data set. That is exactly what we want. So now let's work on creating the model, data set model, and then loss. So it's time for the model. I have created a little helper for you. You've seen this before. This is exactly the same as our cow predictor, but we're going to do something a little bit more intricate with it. Instead of having 2 parameters, we're going to set up a whole bunch. We're going to create a neural network, and PyTorch is very in tune for making these neural networks, and they make it very, very easy for you to do it. That's why, that's what's enabling this course, the tools that they create. So just like before, we're going to call model equals create our model. And we called it a wine predictor. Ooh. I'm gonna ask you guys to change it to diamond predictor. That's a little behind the scenes. Originally, we were predicting wine prices, but the data set wasn't as nice. So we changed it to diamond. So if you chain these, so we need to change the thing in super, the diamond predictor, and on the top to diamond predictor as well. Okay, and then this should work out perfectly. So model equals diamond predictor, open bracket. Okay, just like a function, what that's going to do is it's going to go up to the initialization function. This is a function, and it's going to basically, this is our constructor. If you guys have ever taken a Java class, this is our constructor, and this is where we're going to put some stuff. So just to show, I have been constructed like that. You can see once our model is being made, it goes up to here, it prints out I have been constructed. Okay, so if you remember from last time, our initialization, that is where we're going to put our parameters. So our parameters are going to be very easy. We have parameters in our neural network. So we're going to do this a very easy way. So we are going to do our first layer is going to be, we're going to call it layer 1. Okay, and in PyTorch, they make it very easy to make layers of neural networks. All you have to do is write torch dot nn dot, so torch dot neural network dot linear. Okay, so a neural network layer is also known as a linear component or a linear layer. You can see that it takes in some numbers. The important one for us is that it takes in features and out features. So our first layer is going to take in 24 inputs. That is our diamond data, and it's going to output it to 40 to a layer of 40. So we go up here. Remember, our model takes in 24 inputs, and it has a bunch of hidden dimensions of 40 neurons, 20 neurons, and 10 neurons. Okay, let's do that again. We got to make some more layers, and those layers are going to compound on top of each other. Layer 2 equals torch.nn.linear. And now it is taking in as an input those 40 outputs from the previous layer and transforming into 20 inputs. So it should be pretty obvious about what's happening right now. Okay, we're going to continue this. Layer 3 equals torch.nn.linear. Our third layer will take in 20 inputs, input out 10. Perfect. Our final layer, layer 4, torch.nn.linear, taking 10, and it's going to output to 1. That 1 is going to be our predicted price. How's it going to sit? Okay, awesome. How did you decide how many layers to use? Great point. I was going to talk about this in a little bit, but I can bring it up now. A lot of your job as a deep learning scientist will be trial and error and testing out different layers. This is something I'm actually going to ask you guys, if you go home, have some free time to play around. You can choose a variation of layers. You can try this out with 1,000 layers, going to 500, going to 250, going to 1, or 1,000, going to 2,000, going to, you can choose any number. It's to some point arbitrary. And trial and error, you can make a neural network, train it, see how it works, and maybe it's good, maybe it's too many layers, maybe it's too few layers, but it has a little bit of trial and error. There's no 100% correct answer to the solution. So how did I choose this neural network? Is because I developed this course and I found that this is a good number that will work pretty well. You do have some problems we're going to talk about in the future called underfitting and overfitting. Having a too small of a network can create something that has a lot of bias to it called underfitting. If you have a too big of a network, you can have something called overfitting. And also you have a lot of, if you have a really big network, there's a lot of redundancy. You don't need to have a special laser beam to solve a problem that a pencil can solve. If you're trying to write your name with a laser beam on your test bed, it's a little too intricate. So this is a pretty straightforward problem, but that is a great question, or a great question. In general, one of the properties you want to do with linears is there there's big incentives to try to start with a big amount of hidden layers and work your way down. The intuition of that is that the first layer with 40 input layers, for example, will get small questions. It'll answer those small questions like, for example, is the shape available? For example, what type of shape it is. And then those will compound on top of each other to come to a real solution. So there is incentive to start big and go smaller, but for the most part, it is trial and error, and there's no exact solution. Okay, great question. Okay, so perfect. One other thing I had to say, sorry, I almost missed out on. This is a common error. It's an error I make a little bit as well. You are going to want to do self in front of all these, self dots. That'll assign all of these to be a part of the model itself. Okay, self dot, that's important. Without it, you would run into some errors. Okay, but think about that. We have spent an entire lecture looking at neural networks and their complexities, and we have been able to implement a pretty complicated neural network with a lot of parameters in 4 lines. So PyTorch is a great tool and it can do a lot of things for you. Now we want to be able to use our inputs. So if we run this, it'll go to our initialization and it'll set all those layers up for us. But now we actually want to use them. Okay. So what we're going to do is we're going to take our data set. And what we're going to do is we're going to do data set and index 0. Okay. Let's actually print that out just to show you what it does. Okay. Perfect. So essentially what it's done is if you remember, our data set before, our data set had shape of 7,845 diamonds, and they all had 25 values associated with them. 24 were our features, and one of them is our target. What we did is in this, I said data set, and then in these brackets, just like an array in C, I took the first value of index 0, and this is our first value right here, okay? So this is our target price. This is our normalized caret value. And you can see all of these zeros, this is what we're gonna feed into our network, okay? So what we want to do is we wanna take that, we're gonna say model input equals, and we want it to be this row, okay? Awesome, awesome, perfect. Okay. Cool. So there's one other thing we got to do preliminarily. Our model input, we have to do one other thing to it. We don't want the first value, okay? Because this is actually supposed to be our output. This is our price. This is our price value up here. It's not super obvious, but if you remember looking at our trimmed mystery data set, we are actually looking at, if you look at these values, we're looking at the first example right here. So 0.781, that is our diamond with index 6322, okay? But that is our first diamond in our set. We don't want the price, but we want everything except for the price. So how we do that is we have a model input, and this subscripting we're also gonna have to get used to. We're gonna take everything from index 1, and then if you do this colon right here, what that is telling the input is that it's taking this row and it is grabbing everything from index 1 all the way to the end, to index 25, okay? So now let's print out our model input. Okay. This subscripting is one of those things that you got to get used to in PyTorch. It's a little bit complicated at first, but you'll get used to it. So now you can see we have all of our input data, okay? We have our carets all the way to the end to our round. And we see that this is our round diamond. Its last thing is round. Its other one value up here that has to do with it being a VS1, or sorry, a VVS1. You can see that it has a coloration of F, okay? So this is our first diamond. That is what we're going to use as our input to our model. So if you want to go input to the model, we're going to call our model and we're going to put our model input into it. Okay, perfect as that. Now our model is going to go through forward. We can print out the data. You can see that our forward pass takes one parameter. Our parameter is our model input. Okay, if we run this, let's get rid of this. Don't need that anymore. You can see that we are passing in our model input. It goes up, it runs through the forward. This becomes our model input and it prints it out and we get exactly what we want. This is our 25 values or 24 values that we're going to be putting into our model. Perfect. So how do we actually take that input and put it through those linear layers? And in PyTorch, it is very, very, very simple. Okay, so we're going to transform that data by calling these layers. So we're going to take our data and we're going to say out equals. So that's our out value, or you can call it whatever you want, but it's pretty standard to use out. We're going to say self.layer, and we're just going to put our data through it. Okay, so our data goes in through here. It goes through layer 1, has to be layer 1, and it takes a 24-dimensional vector as an input. That is our model input right here. And it should output a 40-dimensional vector space. So that is the outputs from our hidden layer. So if we run that and we print out the out.shape, we should see it has grown. Perfect. So it takes an input and transforms that into a 40-dimensional vector. And there it is right there. Torch.size is 40. So we're doing a good job. We're going to continue that over and over and over again. Through all the layers. So this is essentially all of the information, all of the activations going through the system. Self.layer 2, data. Sorry, this actually has to be out, okay? Because we're taking in this value right here, into here, and we're going to keep doing that. Out equals self dot layer 3 out, and then out equals self dot layer 4 out. So we have run our data through our model. That's what we've done. And if we are correct, if we've done well, it should print out one value. It should be printing out our one output value, which we talked about, we defined up here. Okay, so we do that and we get one value. We get negative 0.1328. Perfect, okay? It's running through our neural network. We have created a neural network that our data is flowing through, and we've done it perfectly. Please feel free to tell me if anything's an issue in the chat or in person if you're here, of course. But awesome. The one thing we are missing in these is that PyTorch does not do for you, that you have to do for yourself, is after each output, remember it goes through a nonlinearity, and we use sigmoid. So what I'm going to ask for you to do is at the beginning of each one of these, after it gets outputted, so it goes through here, it creates values, we're going to do torch dot sigmoid. Okay, that is going to go through our things and it's going to sigmoid everything. So it's going to put it in between 0 and 1. We've talked about this. Okay, every single output. Perfect.
Sigmoid basically puts it on the non-linearity.
Yes, that is the nonlinearity we're using. Yes, you're bang on the nose. We don't have to put it on the last layer. It's not necessarily required on the last layer. So we're just going to leave it by itself. But that's perfect. That will normalize a lot of our inputs. It will apply our nonlinearity. We run it again. Make sure everything works. That's totally fine. Okay. Our model is not trained right now. Another thing PyTorch does for you is when you create layers using torch.nn, there's a bunch of different functionalities. When we go to convolution, we'll be using convolutional neural networks, and they have tools for you there. This creates a whole bunch of parameters for you. Okay, it does that. It creates the net for you and those parameters, and it initializes those randomly for you. So before, in our last time, we had to manually initialize our parameters. This one will do it randomly, which is exactly what we want. Okay, once we're done here, we're going to return our out. Okay, perfect. We have now created our model. We have created our neural network in a very compact and easy way. Here is our diamond predictor. Okay, so what do we want to do with that? We want to train it, right? Okay, I'm assuming we do. So let's go down, and we've done our data set, done our model. We can get rid of these. We don't need them anymore. That was just for proving it to work. We want our loss. Okay, loss, even easier than before. Loss underscore function. Last week we made our own loss. You guys are smart. You guys have a handle of it. MSc. You guys are pros. You can actually use Torch's embedded loss function. If you do torch.nn.mse loss, it creates it for you. See, we can test it out. If you want to print out, you can put any number in. Remember, loss function takes in 2 numbers. So if you want to test it out with number 1 and the number 0.5, loss function, what is this? You float, object has no size. Oh, you have to put in tensors. We'll talk about that in the future. Don't worry about it. Essentially, but yeah, we now have our MSc loss given to us. We don't have to worry about that in the future. So big thumbs up to that. Easy peasy. So awesome. We have our data set, our diamonds. We now want to train it. So if you remember from before, we are not going to train it on the entire data set. We're going to use a training data set. So it's a subset. We're going to use the first 7,000 diamonds to train our model and the last 845 to test it. So right now we can make a training set very easily by taking our data set, and we're going to take the first 7,000 entrants. So from entrance 0 to 7,000. Perfect. So we can use the last 800 for our testing set. So testing set. equals data set. And we're just gonna get the last one. So from 7,000 to 7,845. That's what we're gonna be looking at. Okay. Now, what I want us to do is just to make sure that we have the right sizes. So training set dot shape. We can copy that as well. Try it out with our testing set. So testing set dot shape. And if we were doing our job, we have 7,000 examples for our training set, and we have 845 examples for our testing set. Perfect. Our data set is ready to go. Okay, awesome. To make this a little bit clear, I also have given you a function for training. We're gonna be using that. Before we do that, one other thing to do, optimizer. Okay, just like last time, it's very easy to use the optimizer. It's torch dot, we'll call it optimizer. Optimizer equals torch dot optim dot, and last week we used SGD, standing for stochastic gradient descent. That is a little bit of an old-fashioned optimizer. Nowadays, we call our friend Adam. There he is. This is a pretty standard optimizer. It's used in a lot of functions. It's called Adam because it was developed by a guy named Adam. And it just so happens to be one of the best optimizers. It deals with a lot of the issues that SGD has, but I gotta tell you, I have no clue how it works. I really have no idea. I know that it does work though. Just like before, we're gonna do model.parameters. That is gonna tell the optimizer, hey, these are the models, or these are the parameters I want you to adjust when I ask you to adjust them. And then we're gonna have a learning rate equals to 0.0001. Okay, so very small learning rate. That is still just a math number. You don't have to worry about it. This should work. Okay, perfect. So now that everything's set up, let's get training. So right here, we're going to set up our training, and we're just going to call this function first. I've cleaned this up a little bit. We're going to be using training functions, and we're going to be using a testing function after. Okay, so we're going to call our training function. It's just called train. It wants your model as a parameter, so let's give it the model. It wants our training data set as a model, as a parameter, so let's give it our training set. It wants our optimizer, so let's give it our optimizer, and our loss function. So let's give it our loss function. Perfect. Okay. So when we get up here, it's going to start running this code. Okay. So starting off, we have gone through this before, the general flow. I'm going to just do it again. You guys should be a little bit used to this. I'm going to reiterate. We can click model.train. If we do model.train, that tells our model, hey, it's time to train. So get ready for that model. And now, like in our example, we want to be taking one row of our data set for input each time. So what we're going to do is do for row in training data set. And what that'll do is it'll take every single row, all 7,000 rows, and it'll take it iteratively. So if we print out row.shape, we're going to see optimizer Adam. Ooh, you know what? Let me see. Is it? I think I made a typo. Model dot. Okay, so let's actually call this. We're gonna change this to diamond model. Okay, it has to do with our Jupyter notebook. It should be. Where diamond? Predictor has. That doesn't sound right. Diamond model underscore predictor. What is the issue here? Sorry guys, just give me 1 second.
You misspelled optimizer.
Oh my gosh. Yeah, there we go. Param matters. There you go. My mistake. Param matters. Ooh, tough one. You know, it's rare you get those mistakes, but yeah, there we go. Okay, perfect. Okay. Let me change that back. Okay, now it should all be working. Yeah, this is exactly what we want. Okay, so what is happening is we are taking our training data set, we are putting it into this function, and it is printing out every single row, the shape of every single row. So each row is of shape 25, and it prints out 7,000 of them. Awesome. So we are iterating through every single diamond in our data set. Perfect. That's what we're looking for. Okay. Now, what do we want to do with these data? We want to find the target and the input. So if you remember, if we print out our rows, remember when we had 25 long and we want to take the first one to be our target. So what we can do very easily is target equals row. The first value in the row, that is our price, that is our target. Okay. I'm also going to ask you to dot unsqueeze 1. Kind of a weird function. I'm going to show you what unsqueeze does. Sorry, it's actually unsqueeze 0. Unsqueeze 0. I'll tell you what that does in a little bit. Actually, not unsqueeze on that one. My mistake. Sorry, I'm a little flustered right now, I guess. Our input is going to be equal to row, and it's going to be 1 all the way to the 25th. So it's going to take from index 1 all the way to the last one. That one is the one that we are going to unsqueeze. Okay, and I'm going to get into that in 1 second. So perfect. So if we print out our target, we can also print out our input. Let's see if it's working. We can also print out target.shape and print out our input.shape. Okay, I'm also going to call break after this, just so we don't go through everything. We only go through one example. Type error, unsqueeze, or unsqueeze 0. Unsqueeze 0. Perfect. Okay, so let's see what's happening. Our target, we get one value, 0.781. That's exactly what we're looking for. Perfect. Our input is the rest of the values. Awesome. Also what we're looking for. And let's look at the shape. So the shape of the input is just, it's a scalar number, so it has no dimensionality. And what unsqueeze does, okay, and this is a little bit interesting. It doesn't make a whole lot of sense until we get into mini batching, which is a concept in the future that's very important to data scientists. But a lot of these torch functions, they ask you to input data in a form like this. So if you want to read this, it says, I have one diamond that has 24 features to it. That's what it's looking at. If you just passed in 24 features without saying I have one, you get errors. Because in the future, what's going to happen is when you mini batch, a lot of the time, when you're training, you'll hand in 32 different diamonds to the model at once, and it helps the computational speed. So that is our batch size, what it's called. Don't worry about it too much. You just got to know that it works. Okay, how perfect is that? Okay, awesome. So we're also going to do that for our target. We're going to unsqueeze it. And I'm doing that because I want to show you what that does. Okay, so now before you can see that it's 0-dimensional, it's a scalar. If you unsqueeze it, it adds a dimension to it. So now we can say we have one value for output, and that value is 1-dimensional. Awesome. Through training, now we can get to the juicy part. Okay, we are going to use our model to make a prediction. So prediction equals model. We've done this before, and we can pass in our input. And if this works correctly, we should get a prediction out of this. So let's print out our prediction. Awesome. So we take our input, it goes through a model, it goes through our neural network in here. That's what this is right here. And it inputs our single value. And that value it inputs is negative 0.7572. So if we unnormalize that, that would be a critically small number. That would be around a diamond, probably around $10, which is really, really not what we're looking for. A very bad guess. Okay, so once we have that prediction, we want to reduce some of the dimensionality. This is an annoying thing that you have to do. Squeeze is the opposite of unsqueeze. It takes out additional dimensionalities. Very annoying that you have to do that. It's just one of those bookkeeping things that PyTorch needs to be able to understand what's going on. Okay, so we have a prediction. Now we can do our loss. Our loss is going to be equals to loss, the loss function. Okay, and our loss function takes a target, and which is this. Remember, that's the price we're going for, and the price that we actually predicted, and it'll tell you how bad we did. So our loss, if we print it out, oopsies, just want this. Just want our loss. Our loss is just a number. Our loss function is the actual function. So remember, our loss function is mean squared error. If we run this code, loss function predicted, not defined. I really got to get better at spelling prediction. There you go. Top it. Happens to every great computer scientist. You can see our loss is 1.2889. When we train this more, you'll actually see that 1.82289 is abysmally high. We did a very bad job, but it's okay because we're going to get better. Okay, now we're going to implement our optimizer. So if you remember from the beginning, the first thing we do is to tell the optimizer, I'm going to give you a new set of data, and you put that at the top and you call optim.0grad. First thing you do, bookkeeping. Awesome. So now it is ready. Now the optimizer starts looking at everything that's happening here. It starts looking at you passing in the data, making the prediction, how wrong that prediction is, and it's keeping track of all of that. To tell the optimizer how wrong you were, remember the loss tells the optimizer how wrong you were. You do loss.backward. That is a back propagation step, which is a mathematical thing, once again. And then once the optimizer gets it, the optimizer knows how much to move. You can tell it to move by doing optimizer.step. And if I wrote this correctly, and my writing has not been terrible, it should work. Okay, so let's print out our loss every single time. Loss.item. That just makes it a little bit more clean. Item, if you remember before, if we don't do this, actually let's do it without it, and then I'll do it with it just to show you what loss.item does. If we run this and we get no errors, it'll keep on going and going and going, and these are the different losses. It should be getting better and better and better. It's a little hard to tell off the get-go because we have so much variation in the data as you go one by one. But it should be quite bad at the beginning, and it should be getting better. Okay, so we mostly just did that to see if it was working, and we found out that it totally is working. So that's great. Once again, let's show you what item does. So remember down here, it says tensor all of this and has all this unnecessary information to it. If you do loss.item, it'll just give you the scalar value. So just for bookkeeping, let's run this to see what happens. Okay, now it's just giving us the value. Okay, perfect. So you guys are learning a lot about PyTorch. Okay, now for this issue, remember what I said before? These models, they'll go through the entire textbook. They'll learn all about it, the textbook from front to back, but they are still quite bad at doing tests after reading it through once. They have to read through it hundreds, tens, if not hundreds, if not thousands of times. What deep learning scientists call that is, for some reason, I don't know why, they're called epochs. So we're gonna do 4 epoch in range, and we're gonna start off by just doing 10. Okay, we're just gonna test out. We're gonna have to do more in the future. Colon, and then take all of this code and dash it forward. So it should look like this. Now we're gonna be running this training cycle. So we ran that training cycle when we printed out all the values. We're gonna be running it 10 times. That's what it does. So epoch fancy name, it literally just means how many times you've gone through it. So at epoch 0, you've gone through it 1 time. At epoch 1, you've gone through it 2 times, and you do that all the way up into epoch 9, so 10 times in a row. What I want to do is I want to see how the loss changes over epoch. So a classic thing you can do is you can put total loss equals 0. So this is actually total epoch loss, if you want to be a little bit more specific. So how much loss is there over the epoch? Okay. What we can do is total epoch loss plus equals loss dot item. So what it's doing is it's looking at the losses of every single diamond, adding it together. So when we get to the end, we can do total epoch loss equals total epoch loss divided by 7,000. Okay. And you guys should be able to realize, or if you guys don't realize, what it's doing is it's looking at the average loss over every single item. So it adds them all together. So that's the sum of all losses. And then it divides by how many times we've done that. So 7,000. Let's print that out after each time. Total epoch loss. And if we're getting smarter, which we hopefully should be, we should see that that our loss starts off quite high and it gets lower and lower. Let's see if that works. Okay. So we're running. This should take a little bit of time. So we start off with 0.9833, and it looks like it is not right now, which is an issue. Okay, but it's an issue we're gonna get through together. Okay, and you'll see why it's not quite working so far. Okay, model.train. Okay, awesome. So let's go to the next step, what we want to work with. Okay, we are going to want to test. So testing. We have another test function. Okay, and in our test function, we're going to pass in the model. We are going to pass in the test data set, and we're going to pass in, oopsies, down here, and we're going to pass in our loss function. Okay, same idea. Okay, so what this is going to do is this is the data we are using to actually train our model. And this is the data that we're going to use to test if our model did well. Okay. So same thing as before, same idea for row in, but instead we're going to be doing in the test data set. Okay. We're going to do the exact same thing with the input and the target. In fact, you can copy that directly if you want, but I'll type it out for just for help. Our input is equal to row 1 to this dot unsqueeze. Just do some bookkeeping, make sure you got it. Unsqueeze at index 0, and our target is equals to row 0, and that's all we need. Okay, prediction, same thing. We want to see how well our prediction is compared to our actual value. So our prediction is going to be equal to model of the inputs. Same thing as before. To be used to it, we can unsqueeze it as well. Unsqueeze it 0. Okay, awesome. So from that, let's print out, let's see if it's working. Prediction and then our target. Okay. Let's get rid of this training right now, and we're just going to test the testing. Okay, so it should run 845 times. Model test data set. Oopsies, I'm really having trouble with my spelling today, or tracking my data set. There you go, testing set. There you go, awesome. So what you're looking at right now is it runs 845 times, and it'll print out the prediction. So our model is not very smart at looking at our variables. So what it's going to do is it's no matter what you input, it's going to output negative 0.75 around. It's just the initialized random variables. It just so happens that that's true. And it's supposed to be getting these values right here. Okay, so we are doing quite a poor job. One other thing I want you to do, sorry, is can you copy this just for, I might run into some errors if you do that. Okay, so just take this, which used to be up here, put that on after the optimizer that step, because that can mess some stuff up in some cases. Okay, so now that we have this, there is a bunch of different reasons why this shouldn't work. These can be quite finicky. Okay, I see. Another small error. I'm gonna have to get through this. So training set, we're not gonna call our model. We are gonna be calling diamond model right up here. Okay, so diamond model. Make sure when you're training, put in the diamond model, and when you're putting the test set, you also want to put in the diamond model. I changed that name and I didn't take that into account. Okay, so let's run this and let's see what we get. Remember, now it's training. It's training. It's going to print out each total epoch loss. So it starts off 0.02. So remember when we first started, that was a very, very high number. It was 1.13. Now it's getting quite smart. So 1.13, it's getting smaller each and every time. So it might not look like big changes. These are actually quite large changes. It's getting smarter and smarter. Now it's what, 0.18, 0.139. You can see that this takes some time, unfortunately. What happens with a lot of these models is as you get deeper and deeper, it gets more complicated. The really high performing models, some of the models that I've worked on, for example, have instead of thousands of variables or parameters, it has billions. So you have to use very strong GPUs, and they can take days to train. This one with 10 epochs, so we trained it over the data 10 times, only takes 52 seconds. Okay, so here are our losses, and here is what our model did. So our model is trying to match these two numbers. And you know what? It has done a decent job. You can see that the numbers and then the number right next to it. So its prediction on the left and its actual result on the right are quite similar. 1.69, 1.626, 1.779, 0.1779 is compared to 0.1720. 0.481 is combined with 0.4540. You can see that the values compared to each other are a lot more similar than they are compared to two different diamonds. So we've actually done a pretty good job. Let's make it a little bit more nuanced. Okay, we have some evidence that our testing set does reflect our model is good on the testing set, and that does reflect that our model is able to pick up on some of the nuances of the diamonds. But let's make it a little bit more interesting, in my opinion. Okay, I'm going to say we got a diamond correct if our predicted value and our actual value are within 20%. So not too big of an issue. So let's make at the beginning of this a correct count. So it's going to start with 0. Okay. Our correct count starts with 0. What we're going to do is we're going to do so target plus 20%. Make our variables very descript in their name. Hello. Is going to be our target value plus 20% of our target value. Awesome. Target minus 20%. Same idea. Target value. Instead, we're going to minus 0.2 of our target value. So what that does is that'll send our ranges. If our prediction falls between target plus 20% and target minus 20%, then we're going to count that as correct. And how we do that is we say if, and if statements look a little bit different in Python. I don't think we've used any yet, but if prediction is greater or greater than or equal than target minus 20%, and prediction is less than or equal to target plus 20%. And that is, I'm sure, an issue you've done before in assignments, trying to see if a number is within a range. It's very common. We're going to say we got it correct. Awesome. Plus equal 1. Perfect. Okay. One other thing I want to see in our test data set is we have our normalized values, which are going to be very hard to read because they're like 0.25. You don't know how much that is in dollar amounts. I have a helper function right here called normalized cost $2. We are going to be using it. So I'm going to say normalized prediction, or sorry, unnormalized prediction. Unnormalized prediction is equal to our prediction inside of the function normalized cost $2. So we're going to take this function and we're going to use it. Here we go. Inputting our prediction, and that should give us a dollar amount. Let's also look at unnormalized target. So this is what we were supposed to hit, remember? Normalized cost $2, and I'll just copy and paste because it's such a long function name. Target. Okay, so now let's get some information, some real information. Let's print out, first of all, prediction.item, target.item. That's going to get rid of all the tensor stuff before, like I said before. Then let's look at the unnormalized prediction. That's going to be our dollar amount. Unnormalized target, we can all add those all in the print statements. Okay, super ideal. And one other thing I want to say is let's tell in our predictions if we got it correct or not. So we're going to make an else statement, and we're going to say is correct. And if it's not correct, we're going to say it's not correct. If it is correct our variable is going to be string that says correct. Okay, perfect. Now, at the very end, is correct. Awesome. Okay, we have one other thing we want to use in our diagnostics. It's nice to get a bunch of information about how well your model is doing and looking at it and putting it in very real human terms that you can understand, because things like loss function and all that stuff, it's very mathematical. It's not quite easy to understand. What we can do is we can print out our model predicted diamonds with a correctness of, do a little comma, and then what we can do is we can do number of correct divided by 845. So if we get everything correct, every single one of them correct, we're gonna have 845 correct diamonds, and we're gonna be 100% correct. Okay, so let's train it. We're gonna train on our 10 epochs again and see how we do. Okay, it does take some time. These things can take some time. So while that's happening, just reiterating on the process, on key concepts. Some of the key concepts I want you to understand is working in data sets. We're going to be doing this scripting a lot. You are going to get used to it. In this, it says take data set from index 0 to index actually 6,999, but it takes the first 7,000. This one goes from index 7,000 all the way to the end. It helps us slice our data apart. Perfect. Optimizer, you guys are used to. Training, this is pretty straightforward, what we've done before. It's just using our optimizer, running it through the loss, calculating the loss, giving it to the optimizer and propagating, and seeing the results we get. Okay, here we go. It's ready. So if we go to the top, we can see it's trained. We can see we have good results because our loss keeps on getting lower and lower and lower. Okay, now let's look at what we're printing out. So if you remember, prediction.item, these are the normalized values. These values should be quite similar, and it looks like they are. Here are our dollar amounts. I should have just for next time to make it a little bit easier, we're also going to print out item just to get rid of that tensor board. It's a little bit ugly to look at. Just for next time. But we can predict this was $1,000, $1,970 diamond, and we predicted $1,997. We were very close to being correct. If we go through all of this, we can go through all of this different data and we can see that we're getting a lot of them correct. And that is actually quite amazing. If we go down to the absolute bottom, we should see how much we have correct. So we have a correctness, we get about 75% correct. So that's pretty good. I am impressed with that. Our model predicted the diamonds with a correctness of 0.75%. So 0.75% or 75% of all of our diamonds fit within 20% of their actual value. I think we did a good job. Now, one thing that's fun to play around with, especially if you want to go home or right now and play around with, you can see how different things affect. The one thing I say would probably affect this the most is if you change the number of epochs, okay? If we run this 100 times, if we can see, it's going to take a long time. I think in my calculations when I was running this before, it should take about 10-ish minutes to train. But retraining it over and over and over again, you will get better results up to a certain point, okay? Another thing that's fun to play with, try making bigger nets. You guys know how to make neural networks now. You can't change this value. You can't change this value, but you can change all of the other values in between. You can try, if you want to, you can try with 1,000 and 1,000 going to 500, right? That 500 going to 200, that 200 going to the final output neuron. You can add more layers if you want. You can do, instead of layer 3, you can do layer 3 here or layer 4 here, and then having a 5th layer, copying that over. 4, and then 5, okay? Like these are very easy to change around. That's why a lot of deep learning scientists love this. It's very easy to implement new models and different characteristics and see how that affects your data. Because a lot of the time when you're really trying to get the best performing models, you want to see how different hyperparameters, what we call it. So number of epochs is one of the hyperparameters that the scientists can choose to use. Learning rate is one of them. Playing around with learning rate is also very fun. Having a higher learning rate will make your model learn faster, but it can also lead to very unpredictable behavior. If you have a lower learning rate, it's going to be very slow, but it's going to be more precise. These are the things I think you should play around with. Learning rate, playing around with the net itself is very, very fun and interesting to do. Yeah, I think it's great. You can try out different optimizers as well. That shouldn't make too big of a difference. But you could change this out to standard stochastic gradient descent easily. And they'll all have different effects, right? So even though it has the word science in it, like data science and all that stuff, this is not an exact science at all. A lot of this has to do with making guesses, and it becomes very inexact. It does depend a little bit on randomness, because if you remember, all of our parameters are computed completely randomly. And it can just so happen that if you run it again, you could get a worse model or a better model. There shouldn't be too much variation in that, but there is a random component to it. It's not exact. You are going to get some right, some wrong a lot of the time. It's very rare to have a machine deep learning algorithm that can do anything interesting, be 100% correct all the time. But you can see that our loss, even we did first 10 in our first 10 examples, you can see that it went from this number all the way to 0.0008051. That still is going down now. It is getting smarter and smarter and smarter. And actually, you should see that it is not learning as fast. Obviously, like there's a lot more of a change stepping from epoch 0 to epoch 1, but this is getting exponentially smarter. And I would expect better results coming out of that. Okay. I am going to ask if you guys have any questions immediately. I think that'd be great. But that is basically what we're doing today. So normalization, big concept, neural networks, biggest concept. And I hope you had a little bit of intuition of training and testing. But that is going to be it for today. 2 hours, exactly what I was looking for. Let me know if you have any questions. Perfect. Next week, we are going to be running through neural networks again. It is going to be a little bit more hands-on. We're going to be working with I think a very interesting data set. We're actually going to be working with using handwriting, predicting handwriting. So if I give you pixel values with the number 2 on it, trying to predict, is that the number 2? It's a very classic problem, and it has a lot of implications in the real world. So we're finally getting away from ugly data sets, tables of numbers, and getting to something a little bit more visual, a little bit more interesting, and a little bit more fun. We're also going to be learning how torch.nn.linear works. We are going to be creating our own version of that, and it should be fun. So thank you, everybody, for coming today. That's it. If we don't have any other questions, same time next week, same link, same everything. Awesome for you guys to come through. Appreciate you guys coming here. And I hope you learned something pretty cool. This is when the course really starts ramping up a little bit, in my opinion. You have all of my social media and you have all of my email. So if you have any questions, if anything flew over your head or is a little bit tough to understand, something you have question marks about, please email me. Yes, Sarah. Okay, I can totally do that. I'm actually going to be posting the slideshows and also the code. Okay, so the one place I want you guys to look on from now on is if you go to the instagram.com/braintankdeeplearning. I know most of you guys should have Instagram of some sort. If you go there, I am going to be using this link system. Linktree, you've probably seen it before, and that I'm going to devise a way to post all of our slides up here. If you don't have Instagram, I'll just send you the link. Just send me an email. It's totally fine. But I think most of you do. I know a lot of people signed up through Instagram. So right now we have the YouTube links from the previous workshops and also our Zoom link, which we're using today. Excuse me. Yeah, so there we are. Here's our first video right here. So you can look that up. Our second video is going to be on today. I had some issue uploading it last time, but I got it figured out, so it should be up a lot sooner. Okay, other than that, if you have no questions, thank you so much for coming. Thank you so much for taking time out of your day and learning. I think that's so great. And I will see you guys next week. I'm so excited to see you there. Okay, perfect. See you guys. Bye. Awesome. Okay, here we are.